So we saw that if there is a direct mapped cache, then the address would be mapped something like this. The lowest few address bits will be used to identify which byte is being addressed from the cache memory, and the higher order address bits are put as tags. So you see 5 address bits are being used to select one of the bytes in a particular block. And cache index says which block we are which block we are interested in. The cache tag stores the higher order address bits, which are used to match which addresses or which physical address is being put into the cache there. Do you remember this slide? We had covered this in the last one. Any questions about this? So silence, I cannot make out. I cannot read your silence at all. This means yes, this means no. I do not know. Hello?
Sir, can you explain again this one second part? Like 4 bytes you are selecting for the byte select, then the remaining for the cache select.
So not 4 bytes for the byte select, 5 bytes for the byte select, because there are 32 bytes in one line. Addresses 0 to 4. So there are 5 address bits that are used to do the byte select.
Okay.
The remaining 5 bits are used to select which line we are talking about.
Okay.
This is clear?
Yes, sir.
Okay. Then once this is clear, what is the next thing that we look at? We looked at where, in which parts would this data be stored. So which parts would this data be stored? Suppose my byte address is, the last few bits are 00000. So where would this data be stored?
Sir,
Are you writing something? Your screen went
sir,
blank.
your slide is not visible.
Your slide is not visible.
Oh, just give me a second. Just a second.
Sir, it can be at 0, 16.
Can be at
0, 16.
Yeah. So what we are looking at was, are you able to see the slide now?
Yes, sir.
Yes, sir.
Yeah. So what we were looking at was, depending on the last bits of your address in the cache, your memory would go into one of the given rows. Your entry, your data could go into one of the given rows. So what we were saying was that these grays can only go into this location. Now let us say there was a program that was using this set of data, and there was another program which was using this set of data. Now this gray and this gray are in conflict with each other. So when this program is being executed, this gray will see a miss. It will fetch the data from the L2 cache and execute. Then as soon as this program gets the priority, again this will see a miss. So it will have to again access the L2 cache and get the data back. So in a direct mapped caches, there is a clear, distinct possibility of lots of conflicts, due to which there can be misses. Are you able to see this?
Yes, sir.
This is the slide we saw last time also. So what we were saying was that conflict misses are caused by different memory locations mapped to the same cache index. And there could be two solutions: make the cache size bigger or use multiple entries for the same cache index. Now, using multiple entries for the same cache index, what does it mean? That at the same cache index, more than one kind of address can be saved. What did we say here? We said that only 001 settings can go here. If I say multiple entries, then even though this address is 001, I would say that it can, if need be, let us say also store 011 or 111, let us say. If need be, it can store those two also, but primarily it will store this. So if I start to do it like this, then what happens? Then when this other address or when this other data had to be written, and I saw that this was a valid entry and it was very recently used, then I say, okay, let me write it here in the other location in the cache. So I will not have a mess. I will not be playing the ping pong game that, okay, every time the program changes, there are lots of messes and there's a loss in throughput. That will not happen any longer. Ideally, if I can just put any address anywhere, then that is the best utilization of the entire L1 cache space. Are you able to see this? See, if any address could go anywhere, so we're not talking